Hi everyone. Let's have a look at the first question for the first week of homework. Looking at the ordinary level question first. You'll have to forgive me, I'm a bit rusty on doing some of this. This might not be the slickest production ever, but sure, let's give it a whirl. Okay, so this is ordinary level 2020 question 6. And the first of the theory questions is always a mechanics based one, and this was no exception. So let's have a look. Sir Isaac Newton was an English mathematician and physicist. He is widely recognized as one of the most influential scientists of all time. Newton's first law of motion states that a body remains at rest or moving at constant velocity unless an unbalanced external force acts on it. Okay, the first thing you're asked to do, and you always just scan for at ordinary level, they'll kind of point out when they want you to do stuff, just scan for these numbers down the side and you have to do something to earn those numbers. So let's look, a block weighs 400 newtons. A crane lifts the block so that it moves upward with constant velocity. So it's not accelerating, it's moving at the same velocity. Use Newton's first law of motion to find the force that the crane puts on the block. Well, here's the thing. Even if you're a bit rusty on the rules or the forces, if you just look at this first block of information, they kind of give you a big hint there. So if something's moving at constant velocity, that means that the forces acting on it are balanced. So if the block weighs 400 newtons, the force acting on it from the crane is also 400 newtons. So it's a 400 newton force. That will mean it's moving it up at a constant velocity. Now I'm just going to kind of verbally say the answers as well as writing some questions here, but that's what you need to say for that one. So because it's moving at constant velocity, the forces are balanced, therefore it's applying a force of 400 newtons, and that's the first bit done, 6 points. Excuse me, Newton's second law of motion states that the force of an object is proportional to its rate of change of momentum. So you apply a force to an object, it's going to change its momentum, it's going to accelerate. If you have a bigger force, will cause a bigger acceleration. That's the core of it. So here we've got an object of mass 9 kilograms and it's subject to 3 forces. A 6 newtons force pulling it to the left and 2 forces pushing it to the right, a 5 newton and a 3 newton. We're asked to calculate the resultant or net force on the 9 kilogram object in the diagram above. So overall, what force is it going to be subjected to? Well, you've got 8 moving in that direction versus 6 in that direction. So overall, it's the 8 newtons trying to pull it to the right, minus those 6 that's going to try and pull it to the left. And overall, you've got a 2 newton force pulling it to the right. That's all they want from that. Excuse me. Okay, part 3. Calculate the acceleration of the 9 kilogram object. All right, well, this comes down to the special case of Newton's second law. So this is F equals ma. Now, I'm not just pulling it out of thin air. You have that in your logbooks. Now, unfortunately, guys, I made a version of this video earlier, but my computer crashed out, and I didn't realize I don't have logbooks at home. I did that one in school. So I was hoping to show you exactly where to find this stuff, and hopefully as I say, it's early days yet, we'll get familiar with it. But this section, it's in the physics part of log tables around page 50. Most of these formulae come from. You don't have to memorize them, okay? So even when you're doing these practice questions, you have the same resources that you would on the day. So have your logbooks with you, and they have so much information to hand. Okay, so F equals ma is what we need here, because we're looking for the acceleration. We know the force is going to be 2 newtons. We know the mass is 9 kilograms. We're just looking for the acceleration. So we're just going to do a small bit of rearranging here. Let's bring that m across, or alternatively, you can say we divide both sides by mass. Excuse me, giving us F over m is equal to 8. So that's either dividing both sides by mass cancels off and you've got F over m here. Or if you prefer thinking about as bringing across the equal sign, is multiplied by here, it becomes divide by there. So F over m equals 8. The force is 2 newtons. The acceleration, the mass is 9 kgs, which gives us an acceleration of, now it's going to be a bit controversial here. You can actually leave it as a fraction if you want. You can say it's 2 over 9, and then you've got to remember that the unit for acceleration is meters per second squared. Or, if you don't like that fraction, which most people don't, just go 2 divided by 9. And your calculator is going to want to keep it as 2 over 9 because that's like the purest version of the answer. But if you press the SD button, it'll say it's 0.2 recurring. That little dot just means that it's 0.22222. So 0.2 recurring meters per second squared. That's the acceleration of the 9 kg object. I should really kind of, that's part 3. As I say, I'm a bit rusty at this, guy, so if you're looking at the visual of this, it's probably hard to keep track of what's going on, but let's do this one here. Okay, state Newton's third law of motion. That's the equal and opposite reaction one. So for every action, there's an equal and opposite reaction is one, but a more exact version is that if body A exerts a force on body B will exert a force on body A that's equal in magnitude but opposite in direction. That's a bit more precise, but it's the same vibe. So for every action, there's an equal and opposite reaction. Or if body A exerts a force on body B will exert a force on body A that's equal in magnitude, so the same size, but opposite in direction. Part V, use Newton's third law to explain how a rocket takes off. A label diagram may help your answer. Okay, whenever they say a label diagram may help your answer, they really do mean it, so don't be afraid to lash one in. So for a rocket, it doesn't have to be a masterpiece, just a little stylized rocket. The kind of stuff coming out the bottom, it isn't like fire. That's a cloud of gas that it expels. And what happens is the rocket pushes out the gas. It exerts a force on the gas, pushing it outward. And at the same time, because for every action there's an equal and opposite reaction, the column of gas exerts a force upward on the rocket, pushing it up. And that's how the rocket gets moving. Okay, we're on to the last little section here. And you might notice they're kind of distinct. So even if you struggled with this previous bit, this is kind of its own animal. So a car of mass 700 kilograms at rest. It accelerates at a constant rate for 6 seconds until it is travelling at a velocity of 18 meters per second. Calculate the kinetic energy of the car when it is travelling at 18 meters per second. Okay, so straight away, I don't expect you to remember all these formulae. Remember, they're in the logbooks. Around page 50-ish. So let's get the kinetic energy one. Kinetic energy is half the mass times the square of the velocity. Will give you the kinetic energy. I'd get in the habit of, whenever you're doing these kind of questions, when you identify which formula might be useful, write it out before you do anything else to it so the examiner can see what you're doing. And then also just write out the known quantities. So here we know the mass of the car is 700 kgs. So let's just put that down. Kind of like the SUVAT stuff we did last year. In fact, very similar. It's going to be the same. Okay, so we have the mass of the car is 700 kgs. We don't need the full SUVAT stuff yet because we're just looking for kinetic energy. We just need this final velocity, which is 18 meters per second. And now let's plug those numbers in. So the kinetic energy of the car is half times 700 times the 18 squared. A lot of people forget to do the half and make a silly mistake there, so just be on your game. So I'm going to say 0.5 for the half, multiplied by 700 kgs of the car, times 18 meters per second squared, meters per second, beg your pardon, and it's going to be squared. And that's going to give us an answer of 113,400. Don't forget, you always have to include your unit. Because this is an energy value, this is joules, so J for joules. Okay, hopefully that's kind of visible there. I think I might have washed out the image. Okay, 113,400 joules, that's the kinetic energy of the car when it's moving at that velocity. Okay, part VII, calculate the acceleration of the car. This is a SUVAT question, okay? So treat it like you would all the ones we practiced. Write out SUVAT. This is the constant motion equation, standard of motion. So S is the distance the car travels. Now we don't know that, and frankly this question, it doesn't look like it's asking for it, so leave it blank for now. The initial velocity, well, they say that the car starts at rest. That means its initial velocity is 0 meters per second. Its final velocity is 18 meters per second. Acceleration is what we're looking for, that's what we're tasked with. And t, the time, is 6 seconds. So again, you're going to need to find which of the kind of motion equations is going to be most useful. Now, there's two ways of looking at this. The one we're going to look for here is v equals u plus at. That's the one they give you. But that's actually a special, that's kind of derived from what acceleration is. And if you think about what acceleration is a change in velocity over time. You know, if you go from 0 to 60 and how long, think about cars. So acceleration is actually v minus u over t. You can look at that as being a rearrangement of that, but actually, this one comes from that. So this is kind of what acceleration is. Final velocity minus initial velocity over time. And that's what we're going to use. So we're looking for the acceleration of the car. Well, that's v minus u, so that's 18 minus 0 over t of 6. That's in meters per second, that's in seconds. 18 divided by 6 is 3. And let's just think about the units for a minute. We know that the answer to this should be meters per second squared, because that's the unit for acceleration. Let's just make sure. Meters per second divided by another time unit of seconds becomes meters per second squared. So the units check out. There's your final answer. Okay, calculate the net force on the car as it accelerates. They're just playing with F equals ma again. So we have a mass of 700. We have an acceleration of 3 meters per second squared. Sorry, 700 kgs. So don't forget your units. So the force is a mass of 700 times 3 meters per second squared. That's 2100 newtons. So that's the answer to part B, Captain. Okay. Now the last two. Okay, bit more tricky, and that's because it's the end of the question, and they're going to try and challenge you a little bit more. The engine of the car provides a driving force of 3,000 newtons. Now look, it might seem kind of patronizing, but I'm always going to sketch this out. I have to. It's the only way I can picture this in my brain, and it always helps. Do a little diagram, even if it's something as simple as that. Okay, so we have the car's engine providing a forward force of 3,000 newtons. Now, if you're thinking about the force from the engine, that's going to be opposed. When you try moving stuff, some forces try opposing that motion, namely friction. So friction between the tires and the road, or friction from the air around it hitting the car. So there's a force kind of slowing things down here. And whatever that force is, we only get 2100 newtons of actual forward motion. So what that's telling us is that the missing 900 newtons, that's what the friction is. So calculate the friction acting on the car, it's 900 newtons. Because it should have 3000 newtons from the engine, but we're only getting 2100. That's down to 900 newtons being lost to friction. And finally, part X, state one method of reducing friction lubrication using some oil will reduce friction. Okay, I'm going to break this video into two parts. That's the ordinary level question, and hopefully it was useful. I'm going to keep this as brief as I can, so I'll talk to you soon. Bye.